Let's talk about combining functions and application problems. To begin with, let's look at an example of composition of functions. Remember, composition of functions is where I nest one function inside of another, such as f of g of x. Let's look at an example. Suppose I have the functions f of x equals square root of x and g of x equals x squared plus 5. Then we could find the composition, f of g of x, as follows. Well, first, since I want to find f of g of x, that means within my function f, everywhere I had an x, I'm going to replace it with g of x. So for my function, that would look like the square root of, instead of x, we replace it with g of x. In this case, that would be the square root of x squared plus 5. Similarly, suppose I wanted to find g of f of x, I would do the same thing. Namely, in my function g, everywhere I have an x, I'm going to replace it with f of x. So that would look like f of x quantity squared plus 5, and then I'll replace my f of x with what it is, namely the square root of x all squared plus 5, and you could simplify that to x plus 5 if you like. So composition allows us to combine two functions. This can be useful for some real-world problems. Let me show you what this looks like in an application example. A farmer has 2,400 feet of fencing and wants to enclose a rectangular field with one side on a river. Find a function for the area of the field in terms of the length of the side parallel to the river. We have a little diagram here to help us understand what this problem is asking us for. Notice we have a river on one side and then fencing on the other two sides. To begin, let's give this figure some names. We'll call that side L, the one parallel to the river, and since this is a rectangle, the other two sides must be the same length, we'll call those W. Alright, let's start using the information in the problem. Well, I know that the total fencing I have available is 2,400. And if you look at my diagram, 2,400 feet of fencing would be the red part. Namely, I have an L and two W's. So that gives me one expression, and now I'm asked to find a function for the area of the field. Well, what do we know about area? Well, the area of a rectangle should be equal to length times width. In terms of the variables I've given, that would just be L times W. Alright, well, we want to write the area just in terms of the length of the side parallel to the river. That's L. So I want to write A as a function of L. The problem is, right now my area has both L's and W's. So what I'm going to do is I'm going to use my first equation to eliminate W so that I can substitute in the second equation and only have L's left. Let's look at how we do that. So our elimination step would be start with this equation, and we want to get rid of the W because we don't want the W to be in our final answer because we want A of L. So if I do that, I can solve for W. That would be 2,400 minus L divided by 2. And now I can use substitution to put this into my second equation. So I know that area is equal to length times width. And since I just want everything in terms of the length, I can replace the width with that whole expression we just found. 2,400 minus L all over 2. Now I have an expression for A just in terms of the length, namely L times 2,400 minus L over 2. And that then would be the answer to the problem I've been asked. This in and of itself isn't very interesting, but what I might be able to do is use calculus to find the largest such field that I can enclose with my given amount of fencing. And that starts to get into something called optimization, which is a very useful tool. All right, let's talk about a general approach for solving these types of problems. The first step is to identify the relevant variables. For our previous problem, we had length, width, area, and perimeter, which I called total fencing. All right, once we did that, we wanted to write one or more equations relating the identified variables to each other. Those were our equations that area equaled length times width, and the perimeter, or the total fencing, we had 2,400 square feet available, and that was equal to the one side of length L plus the two sides of length W. We chose our dependent and independent variables. We wrote A should be a function of L based on the description of the problem. And then we went back and said, if I just want A of L, I don't care about W. So I went back and eliminated W. W was my unneeded variable, and I identified that W was equal to 2,400 minus L all over 2. And then finally the last step was I substituted that unneeded variable into the desired equation. The desired equation was for area, so I wrote that area was equal to length times width, and my width was 2,400 minus L all over 2. So those are kind of the general steps that we'll use when solving these problems which require multiple equations to be combined into one. Let's look at another example. A rectangular box has a square base. The volume of the box is 60 cubic feet. Find a function that models the surface area of the box in terms of the length of one of its sides. Since this is describing a geometric figure, let's begin by sketching a little version of it for ourselves. I'm going to draw my square base and then turn this thing into a box. Let's go ahead and go through the solution process. The first step is to identify the relevant variables. On my diagram over here, I'm told the length of one of the sides of the base is x, and since it's a square, that side should be x too. Also, I probably need a way to refer to the height of the box, so I'm going to label the height h. So if we want to identify the relevant variables, I have my side lengths, x and h. Since I'm talking about volume, I probably need something to refer to volume. I'll call it V. And we're also talking about surface area, so I'll use the letter S to refer to our surface area. The next step is we'd like to write one or more equations relating the identified variables to each other. Let's start with volume. What do you know about volume of a box? Well, volume is length times width times height. In this case, my length and my width are both x, and the height is h. I could simplify that as x squared h. I also want to find an equation for the surface area. This is a little trickier. Let's break it down. If you look at the top and the bottom of the box, each of those surfaces has an area of x squared because it's length times width, so the area of each of those shaded regions is x squared. And I've got 2 of them. So I have 2x squareds, and then I have 4 remaining sides of the box, each of which is an x by h rectangle. So that would be 4xh. So now I have an expression for volume and one for surface area. Let's now choose the dependent and independent variables. For this, I need to go back and read the problem and see what it is I want. I want a function for the surface area in terms of x. So that means I want to find s of x. Now we can solve one of the equations for an unneeded variable. Well, the unneeded variable in this case is probably our h. We don't need to use that h value to get s of x, because my s function here has both x and h, but I only want x's. So let's use the other equation, volume equals x squared h, to help eliminate the h's. In the problem, I'm told the volume is 60 cubic feet. So I can use now that 60 equals x squared h, or solving this gives me h equals 60 divided by x squared. Finally, the last step in our problem is to use substitution to replace the unneeded variable in our desired equation. Desired equation just always means what is it the problem is actually asking for. In this case, s of x. So I'm going to try to find s of x, and I'm going to write down my s expression, 2x squared plus 4x. Oops, I don't want h, so I'll replace it with my nice simplified term, 60 over x squared. And now I know I'm done because I have a single variable on the right-hand side. Everything for the surface area is written in terms of x. You could simplify and cancel an x there, but for now, we'll go ahead and stop there. Alright, once you've finished one of these types of problems, you probably want to check your function. You can try a test point, check the sign, check to make sure the dimensions are correct, and check the domain of the problem. You're now ready to try some of these on your own. Thanks, and happy learning!